registration. I'm a professor at Queen's University in Kingston, Ontario, Canada, and currently serve as president of IGS North America. IGS North America is the North American chapter of the International Geosynthetic Society. Our mission is to provide leadership in advancing geosynthetics education and research. We are committed to providing high-quality technical training like today's webinar. Similarly, I'm also very happy to report a very successful Educate the Educators event held last December, where we provided training and educational materials to 35 engineering professors from across the United States and Canada to enable them to offer state-of-the-practice geosynthetics education to their students at their universities. We are the Learned Society for Geosynthetics in North America. Our members are engineers, educators, manufacturers, contractors, regulators, and researchers, collectively dedicated to creating opportunities for sharing new knowledge and developing a better understanding of geosynthetics. Learned societies need learned members, so I ask you to renew your membership for 2018 or encourage you to consider joining us. Our website details the many benefits of being a member. Thank you for that consideration. I am now very pleased to introduce today's speaker, Richard Thiel, President of Thiel Engineering. Rick is an engineer with over 30 years experience in containment design applications for geotechnical projects, waste containment, secondary containment of fuel, and leach mining applications. He has participated extensively in the feasibility evaluation, permitting, design, and construction of waste facilities and surface impoundments. He is a leading practitioner who uniquely and valuably shares his insights and experiences with our profession through conference and journal papers, short courses, and panel discussions. Personally, my own research and teaching efforts on geosynthetic liners have benefited from his contributions. Like you, I await his presentation today on pond liner system design and operation. Ladies and gentlemen, Mr. Richard Thiel.
Well, thank you very much, Richard. It's quite inspiring to see so many participants from friends and colleagues all over the world. It's really a testament to what we're doing here. I see some people are having problems with their audio. All I can say is it's very clear for me. I hope you can work your way through it. So I have a series of 57 slides. It will take a full hour to present. If along the way you have questions, I encourage you to type them in, and I will try to monitor them as I'm talking and answer them on the fly or else catch up at the end. So it's designed to be an hour and a half, and we'll see how it goes. I just want to make one little caveat that my presentation has a mix of units. I do virtually all of my design work in English units, and I write all my papers typically in SI units, and most of the world works in SI. So I end up talking in both, and you'll just have to work with that and try to sort it out for yourself. Okay. So the webinar is about ponds, and there's other names for ponds. We also call them surface impoundments or reservoirs. And in the context of this presentation, they're completely synonymous terms. I've worked on these types of facilities virtually my whole career. I started out designing, being a staff engineer for large dams and very large reservoirs. But most of my career, in fact, has been involved with the containment industry where liner systems have been used. And in that context, most of the reservoirs I've worked on have in fact been called more surface impoundments or ponds. And I'm going to use the word pond for the rest of this talk. This slide presents an outline of my talk. There's 6 quasi-technical topics. I won't be able to go very deep into all of them because of time constraints. And so we'll dive into it on the first topic of the geotechnical concerns with ponds. So I have four geotechnical concerns that I typically think about when designing a pond. And the first one has to do with understanding the hydrogeology and the geology that's going to occur below your facility. And it's very important to understand where high groundwater will be, especially when you have a lined pond. So don't dare design a lined surface impoundment or pond without understanding where the high groundwater will exist, because that has a lot of influence on consequences that can occur with your lining system. So typically you do some borings and you understand the geology and the hydrogeology. Typically the project will involve excavation of the soils and embankment construction to create the dikes for the pond. The soil type will influence how the dikes react against loading conditions for the potential saturation, for slope stability, and for the subgrade preparation for the lining system. So understanding the soils that you're working with is very important. The perimeter dikes have to survive various conditions, including wind and waves, which we'll talk about later. And it's ideal to have some cohesive elements to your soils that create your dikes. And we'll discuss that a little bit later. And then finally, the global stability analysis of the pond structures is an important aspect of every project. And you can have whole courses just on global stability analyses. I just wanted to mention that relative to liner systems in ponds, the standard engineering approach is to assume that there is no liner extant when you're doing your global stability analysis. There have been a number of case histories showing that, in fact, a full phreatic condition can occur through the perimeter dikes as if the liner's not there. And so it's incumbent upon you to consider that standard industry practice is to assume the development of a full phreatic surface. This slide shows, for example, the blue line, that's the phantom line. On the right-hand side is the water surface in the pond, and then it creates a phreatic surface through the perimeter dike. And you would conduct your slope stability analysis assuming that. Okay, if you don't assume that, you're not following industry practice, and there have been demonstrated failures because that was not considered. All right. Part two of the outline is how to decide on what your liner configuration would be. Later on, we'll discuss perhaps choosing a type of geomembrane. That's not what I'm talking about now. It's what is the configuration of the liner system? You could say no liner system. For example, on the very large dams and large reservoirs, typically they're earthen or concrete dams, but you don't have necessarily a liner all the time. But this webinar is focused on ponds that do in fact have geosynthetic liner systems. So you could have a liner configuration that has a single geomembrane, for example. You could have a double liner system with a leakage collection layer in between, which is very common for most important ponds. Then for the upper geomembrane, do you leave it exposed, which is very common for reasons of capacity and cost, or do you cover it with soil to protect it? There's various reasons we'll go over later, but if you protect it with a ballast layer, that's a very key decision to make up front. And then finally, is there a need to control fluid pressures below the liner system? You may have high groundwater conditions. You may need to consider controlling leakage through the entire liner system, and you may have air and gas fluid pressures existing. And so you may design some sort of an underdrain. So you have key decisions to make on your liner system configuration. Part of that decision has to do with how you would manage leakage. Leakage is something that I believe is mandatory to consider. J.P. Giroud, considered a father of the geosynthetics industry in many regards, has an adage that the industry holds, many of us believe is true, that all liners leak. No matter what the quality of the initial liner material is, or the level of care that the contractor takes, or the scrutiny of the CQA program, I believe that you should always assume that the liner will leak. And they very often do as they age. There's a lot of emphasis on a push towards zero leakage in the conferences. It seems to be a popular topic. I personally feel that it could lead to some misguidance if people believe too strongly in zero leakage. I think you have to assume there's going to be leakage and wrap your arms around it in all projects. Therefore, you must, I believe it's incumbent upon you to address the consequences of leakage. And once you understand the consequences, then you can make the design decision on your liner system configuration. So I list here 4 consequences of liner leakage in a pond. And what's the difference between a pond, say, and a landfill? One of the key differences is the high head situation. And so the consequences of leakage can be much greater. So certainly we have environmental consequences. If the contained liquid has chemicals in it that would contaminate the soil and the groundwater below, so we all can relate to that. We can have significant geotechnical consequences. Of course, high earth and dams, that's the primary technical issue, are the geotechnical consequences of how seepage occurs through these dams. But in a lined pond, unanticipated leakage can result in piping, tunnel erosion, leading to sinkholes, saturation of the embankment that may not have been anticipated that can lead to slope failures. A third consequence is the operational problems that can occur. One is the loss of valuable solutions in the mining industry or industrial plant, or water for a pond that is a decorative pond, or a pumped storage project where you want that water to be available for the nighttime generation of electricity. Also, if you have leakage, another operational consideration is that you may have to shut down the pond to fix the leak. So these are operational consequences of leakage. A fourth consequence of leakage is that the liner system can be uplifted, either due to buoyancy of the water getting underneath, or the generation of gases, or the exacerbation of liquid and gas interaction causing the liner to be uplifted. So, recognizing those consequences, we could say that there are 4 levels of leakage control. One is none whatsoever. There's no monitoring, there's no collection, you have no idea how much is leaking, and that would have to be a non-critical situation, a decorative pond where you kind of hope to slow down the percolation into the ground, but if there's some leakage, it doesn't have any real consequences. The second level is you might have some control but no real detection and no real collection. So you might design some sort of drainage gallery underneath, but it sort of disappears, and there have been cases where there is confident control of leakage that it will not create a geotechnical problem, but there's no real monitoring. Again, this would be a non-critical situation. Then there's a third level of control where there is perhaps a leaky foundation, say a pond. A lined pond is retrofitted over the top of an old concrete or an old asphalt foundation that's leaky. You have some monitoring, some indication, perhaps some ability to collect the leakage, but it's not pervasive at 100%. And so again, that leakage has to be acceptable. The fourth level of control is for most critical situations where it would be unacceptable to have a significant quantity of uncollected and unquantified leakage. And for most important ponds, this is the case. For most important ponds, you would, by the prior reasoning, you would have to conclude that really the only effective way to know that you're collecting almost all of the leakage and you're able to quantify how much is leaking is to have a complete double liner system with a leakage management layer in between the two liners, such as this diagram shows. For those types of facilities, you would have a double liner with a leakage collection layer between, such as a geonet or a gravel layer. There would be a sump at the low end where you would be able to monitor and pump out the leakage or drain it by gravity. You would have to have a slope typically on the bottom of your pond. And I'm recommending a 1.4% average slope as a somewhat dependable slope to create drainage and to allow for the movement of gas bubbles. If you have less than 1.4%, there have been examples where localized high spots and depressions caused by the grading tolerances and soft subgrades will not give you a dependable drainage and you will not have a dependable mechanism to move bubbles or hippos or whales in the pond. So that's a published number that's been derived, the 1.4%. If you need to make penetrations in these types of ponds, it's generally best to make them perpendicular to the subgrade. That's the best configuration for creating a good penetration and one that can be repaired. If you have an exposed geomembrane in these situations, it's good to have a very strong anchorage so the liner doesn't pull out, mainly due to wind. It's good to have either a conductive liner or the ability to perform electric leak location surveys so that if leakage is detected, you would have the ability to locate those leaks and repair them. I find it beneficial to have a textured liner surface if you're able to on the upper surface. It makes it much safer and more convenient to construct and perform repairs on the pond than having a smooth liner. And finally, perimeter vents, which we'll discuss later, are good on exposed liners to reduce the wind pressures and relieve gas bubbles. If you have a double liner with a leakage detection layer and a collection layer, there's various materials that can be used. You want high transmissivity materials between the liners. Generally, a gravel or a geonet or geocomposite are very dependable materials. I've also actually used the space that's created between two textured geomembranes where one is laid right over the top of the other one, and measured the transmissivity of that space and found it to be quite acceptable. This compares to a poor transmissivity layer, which is sand. Fine sands and medium sands actually impede leakage quite a bit. They don't drain very well, and then you have problems between gas and liquid phases blocking each other's flow. So sand is generally not a good layer between two liners. This slide shows a kind of a dramatic example of a pond I worked on. It was 20 acres in size to contain production water from gas drilling. It was double lined, and this shows pulling one liner over the top of the other using a method called cabling. And the transmissive space between two textured geomembranes was used for the leakage detection. This 20-acre pond was divided into 5 sectors, and one of the sectors, 4 acres, in fact, reported leakage. We were able to estimate the size of the hole by the leakage rate. We were able to locate the hole, and basically it validated this technique of using simply 2 textured geomembranes to provide a transmissive space. So it was a project-specific design. Interesting case history. Now, if you have leakage between your liners, what is an allowable leakage rate? Or sometimes it's called an action leakage rate, the leakage rate at which point you would do something, such as shut down the pond and look for the leak and repair it. So this is a good question. Often it's regulated. It might be written in the permit for the actual facility. There's been various surveys done, and there are various regulations that we can look at. A number of, for example, 5,000 liters per hectare per day, and you divide by 10 to get about 500 gallons per acre per day, is a type of leakage that's common, say, around the Great Lakes of the United States for various types of wastewater ponds. There's an example from Alberta, Canada, for ponds in that region where the allowable leakage rate is the theoretical calculation of leakage through 2 millimeter diameter holes per hectare. The US EPA for wastewater ponds suggests a maximum flow rate leakage rate to be allowed that would result in a 0.3 meter or 12-inch head on the secondary liner. And they provide a suggestion that 10,000 liters per hectare per day, or 1,000 gallons per acre per day, is a suggested upper limit. So those are interesting numbers to consider. Theoretically, what's the maximum that might satisfy that requirement of 0.3 meters of head on the secondary liner? I did a calculation where if you have a double liner system with a high transmissivity geonet between the 2 liners, you can show through a calculation that is described by an article by Giroud et al. In 1997 in Geosynthetics International that a single defect could leak up to more than 50,000 liters per day, just not per hectare, 50,000 liters per day through that single defect, which would be more than 13,000 gallons per day. And the maximum head would occur over that point and would be less than the 0.3 meters. So that kind of gives you the idea of an upper limit. And that amount of leakage could easily be managed in a sump pumping 9 gallons per minute. But what it would suggest is perhaps when you're getting to a flow rate of 3, 4, 5, or 6 gallons a minute, 24 hours a day, 7 days a week, you might want to consider locating that leak and repairing it to stay in compliance and have a secure system where you're not putting too much head on your secondary liner. Okay, let's touch on the question of ballast. Ballast on a liner is a good idea from many points of view. Many owners elect not to put ballast on their liner. Ballast meaning simply a soil covering on the liner, or maybe a riprap covering, or articulated concrete blocks, or geocells that are filled with gravel or cement. Good reasons to put ballast are it provides a pressure on the liner that will create an intimate contact with the subgrade. So all of a sudden, the amount of leakage that would go through the liner would be greatly impeded because of that forced intimate contact between the liner and the subgrade. Also, the contact between the overlying soil and the liner also impedes leakage. So that's one good reason to have ballast. The ballast will also protect the liner from equipment or animals or equipment. So that's a good reason to have ballast. It will largely prevent the generation of bubbles. It'll prevent the liner from uplifting due to gas and air bubbles. And it will also provide ballast to counteract hydrostatic uplift due to groundwater. So these are good reasons to have ballast on liners. Many liner systems, though, are constructed unballasted because the ballast creates a cost to put it in. It uses up a significant, perhaps, amount of capacity in the pond, and it also makes it difficult to repair the liner. Okay, so there are pros and cons to using ballast. Here's an interesting slide from Greg Richardson showing Fabriform, which is grout-filled geotextile mattresses that are pumped in place to protect this wastewater pond, and it protects from the aerator that's shown here, and it also allows you to clean out the sludge that would occur in the pond. I did have one question that showed up here of any opinion on concrete slab ballast. Any type of ballast that you put on or on a liner, yes, any type of ballast on a liner, you have to put the appropriate cushioning layer on the liner to protect it from the ballast. Now, if you have a fine-grained soil, you can probably put that directly on the liner. Things like riprap or articulated concrete blocks or concrete slabs are very good. So my opinion on concrete slab ballast is it's very good. You have to protect the liner from the concrete and place it on there carefully. But once it's on there, it will provide all of those benefits of ballast that we described. And another benefit of ballast, particularly concrete slabs on the slopes, is to protect the perimeter slopes from the action of wind and waves. So yes, concrete ballast is common and it's very good. Thank you for the question. There's a question on rule of thumb for ballast thickness versus uplift pressure. So you have to estimate what that uplift pressure might be. The uplift pressures are from groundwater, elevated groundwater, and so you know what buoyancy pressure is from groundwater. And with soil, it's typically a 2-to-1 ratio of you need about a foot of, well, say a meter of soil would counteract about 2 meters of water, right? Concrete will be more dense. So anyway, it's a simple calculation to counteract the buoyancy of the uplift pressure of groundwater. The uplift pressure of gas bubbles is usually quite small, and we're going to talk about that a little bit. So those would be your most common uplift pressures, and I think they're fairly readily calculated. The hard part is to know what will be the high level of groundwater for your ballast thickness. Okay, so that was the question on uplift pressures. Please continue to send in questions. I'll try to address them. Let's show some examples of ponds that have failed due to poor leakage control. Here is a drinking water reservoir that obviously had a sinkhole developed. This is a single liner system. It had some limited amount of leakage control in the form of strip drains, which I see as a common design in many ponds. People put in, say, geocomposite strips. They'll take a chainsaw and cut up the roll in, say, 2-foot wide pieces and put them at some spacing. I think this pond had them every 30 to 50 feet. I don't remember exactly. And like many drinking water reservoirs, they had a floating cover on top of this one. And to drain the stormwater off the floating cover, in this case, they used scuppers with pipes that went down through the pond and then penetrated the bottom liner and then elbowed and drained out the face of the downstream area of the pond. Well, one of those penetrations, this is the actual penetration, had a leak. The typical location is the sleeve to skirt connection, which is a weak spot. And you could say, well, this is the cause of the pond failure. Yes, but no. I mean, although many of us could design a better penetration detail, in fact, you have to expect that this type of leakage would occur. And so the real reason that this pond failed is that there was not leakage control and leakage management through the liner system, and the leakage consequence was a geotechnical failure. Piping occurred through the bedding in the discharge pipe under the pond. It came out and it partially blew out the face of the dam that was above a town, creating a safety hazard, all because of lack of leakage control. What was the ultimate solution for this drinking water reservoir? It was to put a double liner system with leakage control. Now, somebody says they see geotextiles used below this geomembrane. In my opinion, did this result in increased leakage? Yes or no? The transmissivity of these types of geotextiles is pretty poor. So you would not expect a large amount of leakage to have been caused by this geotextile. It's underneath the geomembrane. And if it had been, say, a geocomposite drainage layer, it might have avoided this sinkhole because it would have routed the leakage perhaps to the strip drains that were, say 5 meters away. And so it would have been more effective if it had provided better drainage. In fact, this geotextile was simply a cushioning material to cushion the subgrade. Okay, so the next case history is a similar case history I got from Greg Richardson, a pond lined in the middle of the Colorado River, a single liner with a penetration around some big inlet or outlet structure, a leak formed in the outlet at the connection to the outlet structure, and there happened to be gap graded soils below the liner system, and so a small sinkhole developed. With the sinkhole, the liner bridged and the water pressure created a catastrophic failure. And you say, well, the problem was leakage at the penetration. Yes, but no. Ultimately, the design, it was incumbent on the design to assume that leakage is going to occur, especially at a connection such as this. The craftsmanship actually was pretty good. The geotechnical consequences were simply not taken into account. What was the ultimate solution for this pond? A double liner with a leakage management layer between the two liner systems. All right, so those were just some interesting case histories showing value of having a leakage management layer. So now we move on to the third topic in the outline, which is liner uplift considerations when you have a pond, especially when you don't have ballast in an exposed pond. I've listed 4 causes of liner uplift: high groundwater, then a localized leak would also perhaps simulate high groundwater, causing buoyancy and uplift in a localized condition. Gas and air bubbles, and then wind also causes uplift, especially when the pond is empty. So here's an example of a pond, it had a thick double liner system, perhaps 1.5 meters thick, and that whole thickness was uplifted by a high groundwater condition. You can see the liner in the middle of the pond being uplifted, and this could potentially damage the liner. In this case, a deep perimeter trench was dug around the pond to lower the groundwater, and the liner just sat right back down and was not damaged. So it's always important to know where your high groundwater is. The other type of fluid is a gas. So you have liquids and gas pressures that can cause uplift. Now the most common uplift problem is gas under a liner is caused during initial deployment. When you deploy a liner, it typically has a certain amount of wrinkles. Well, what is below those wrinkles? It's air. And if the subgrade of the pond is relatively impermeable, or it's a fine-grained soil with capillary water, the air is trapped below the liner, and when you fill the pond, those trapped air wrinkles may coalesce into a bubble. That's the most common source of bubbles on initial filling of a pond. So don't be surprised when your pond initially has a bunch of bubbles in it when you fill it up. The best way is to get rid of those is to have a good slope on your pond, and the bubbles move upslope, and then you have perimeter vents, and the bubbles burp out the vents. Another cause of air or gas bubbles is biological fluids that leak through the liner and then continue to create gas, and the gas is trapped into the liner and it creates a bubble. A third reason is back to groundwater again. Even if the groundwater is below the level of the liner, the action of groundwater rising and falling can push air up during the rising phase and cause bubbles to form. And then finally, I guess there's case histories of volatilization of hydrocarbons or organic decomposition in the soils below a lined pond that can create gases that may create bubbles. All right. Here's a slide showing on initial filling all of these bubbles across the pond. This is a pond that probably does not have a very good bottom slope. In fact, there's a couple very good case histories of this, even when the bottom slope was designed and constructed at 0.75%. That was inadequate to cause the bubbles to move by themselves. And I've got an article series in Geosynthetics magazine now that suggests a 1.4% bottom slope is good to move those bubbles. If you have a leak through your liner and it creates gas, the gas may uplift the geomembrane, and uplift the geomembrane may allow even more leakage to fill the increased area, and even more gas will be created, and it can sort of feed on itself and cause this whale or this bubble to grow. So here's a picture of a wastewater pond with some some bubbles caused by biological gas underneath the liner. So in the past couple of years, I've made what I believe is the first attempt to quantify the levels of pressure, the size of the bubbles, and what the resulting stresses and strains would occur in the liner system as a result of bubbles that are observed in ponds. And the last issue of Geosynthetics magazine and the next two issues will describe all of this. Interesting conclusion is, for example, this is a photo of a pond that has 60 mil HDPE in about 7 feet of water, and the calculations derived by that method indicate that these are on the verge of bursting the geomembrane, like a giant multi-axial burst test. And in fact, that is exactly what happened at this pond. Here's like a 100-foot diameter or 33 meter diameter bubble in 60 mil HDPE in about 1 meter, 3 feet of water on the verge of bursting. Now, look at the pressure, how low it is. 0.2 psi is enough to burst this. If you poke this with a needle, which in fact was done, the pressure is very low, and yet you're about to burst this geomembrane, and it's easily proved. These are some of the results of the calculations that were done. If you just look at, say, the large bubble of 33 meter diameter at the water surface, that's showing in a water depth of just over 1 meter. The diameter of that bubble at the base on the floor is about 36 meters, and it has a pressure of only 1.3 kilopascals, which is slightly less than 0.2 psi. Very low pressure, and that's on the verge of bursting at 12.4% strain. That same size bubble in a half a meter depth of water would only be at about 4% level of strain, and that's what I would consider the maximum allowable state for a bubble. Now go to the other end, where we have the smallest bubble that could be at the maximum pressure condition. That would be a bubble that would, at its base, would be about 8.5 meters in diameter, say close to 30 feet. But the part that's sticking up above the water is this B4 dimension here. That's only 0.28 centimeters, so almost a foot. So it's not peeking out of the water very much. It's in about 2 feet of water, or 2.5 feet of water. If the water keeps raising up to 2.2 meters, say about 7 feet of water, and there's only 20 millimeters of the liner sticking above the liner, and the diameter of that bubble at its base is about 9 meters, again close to 30 feet, that's on the verge of bursting. And so what this shows is, for a 60 mil HDPE liner, if you're going to use a design technique of strip drains underneath the liner to vent gases, they better be closer together than 30 feet or 8 or 9 meters. They should be something like 7.5 meter spacing or 25-foot spacing. Or you might be too far, and you might have a bubble that sets up between your strip drains and causes a failure. Okay, so that's an interesting conclusion of this exercise. So, management option for bubbles, which are very common. There's been several papers written about bubbles. They've been written in the literature for 35 years. To manage bubbles, you need vents around the perimeter of your pond to allow the bubbles to burp out the side. A pond bottom slope of 1.4% on average is a fairly safe, constructible level of building your ponds. and 2% is safer. And that would allow the bubbles to move by the unbalanced hydrostatic pressure caused by the bottom slope. If you decide to use a gas drainage layer at the bottom to move the bubbles, to allow them to vent, that drainage layer must absolutely be maintained in a dry condition. If it's not dry, it will not work. It will only take a few inches of water, or say a couple hundred millimeters of water back pressure, to totally defeat an underdrain to relieve gas pressure. And it's not appreciated how little water would do that. And there's excellent case history of a pond with a complete geocomposite underdrain, 0.75% slope. It did not allow the bubbles to move, and the bubbles got stuck. They had to be pushed out manually, which is number 4. If you see trapped bubbles when you're filling the pond, push them out manually when they're loose. In my papers, I describe how if you keep filling the pond, the bubble gets stiffer and stiffer. It gets more and more difficult to move the bubble until you can't move it, even with several men trying to push on it, and it will cause failure. When they're loose, you can move those bubbles. You can push them manually and work them to the edges. Do not ignore bubbles when they occur. Stop filling the pond and deal with them. That's the bottom line. Okay. And the final uplift consideration is wind, especially when your pond is empty. The effects of wind on exposed geomembrane liners has been well thought out by J.P. Giroud with a seminal paper in 1995 published in Geosynthetic International. There have been several follow-up papers to that one, and the key is basically to look at anchor trenches and the spacing between anchor trenches if you don't have ballast. If you have ballast, that solves this problem. Okay? If you have an exposed geomembrane pond, you do not design your liner to pull out before it rips. You design it so that you give it the full benefit of the strength of the liner. The best reference on designing anchor trenches ever was published by Villard and Charreira in 2004 Canadian Geotechnical Journal. I took off from that and did a few other things in a paper in 2010, but they deserve all the credit for coming up with the best model of how to get the most out of your anchor trench. Then perimeter vents are used not only to burp bubbles, but also they are an antidote to neutralize the airfoil effect due to wind pressures, as shown in this slide. And perimeter vents are easily made by simply cutting a hole. You want to do it at the very top of your liner system, and then putting a patch over the hole where it's only welded on 3 sides. You don't want to put these types of vents too low. This slide from GSI shows how wave action ran water into some of these vents and then caused erosion of the subgrade underneath the liner system. More secure vents are these gooseneck style vents. Enough said on that. Okay, the 4th topic is this aging and durability of exposed geomembranes. The way that an exposed geomembrane ages and in its relative durability, there's 2 aspects to it. One is the chemical and polymeric aging, and the other one is the physical and mechanical durability. The largest degradation mechanism for the polymer is usually attributed to ultraviolet wavelength energy degrading the resin and higher temperatures. And so you get both of those mechanisms with an exposed geomembrane. With UV and oxygen and higher temperatures, you'll get oxidation, and you'll get chemical reactions occurring, hydrolysis, for example, in the resins. It can happen In the dry area, it can happen with the contained fluids. Perhaps there's some chemistry with the fluid itself. And it's especially nasty often at the water line where it gets the wetness and the dryness. Then we have the physical durability challenges caused by wind. Wind flutters the geomembrane. Wrinkles often flutter, and we've seen stress cracking on geomembrane wrinkles that flutter in the waves. You get the tensile forces of the wind pulling on the liner in a very high wind. And hail, I have a slide, I'll show hail damage to liners. There's the cyclic expansion and contraction forces due to temperature fluctuations that cause wrinkles and bridging. Both wrinkles and bridging cause different kinds of stresses and strains on the liner. Wrinkles underwater become fins that are compressed together because of the hydrostatic nature of the water. And so you might get stress cracking at the tips of the fins. And so there's a lot of discussion about how much slack to leave in geomembranes. And I'm starting to believe in these exposed liners, it's better to have a little bit of tension than too many wrinkles. Okay, that's a big discussion in the industry. How much slack to leave? I've got a question here about what about wave action? So I just talked about wave action on wrinkles. It's very detrimental, and I'll talk about wave action more on the perimeter of the reservoir a little bit later. Ice, when it forms, it can be pushed around by the wind and physically bang against the liner, so that can be detrimental. And then, of course, there's animals, including humans, walking on the liner, walking in the pond, equipment, the use of pumps, boats, cleaning, all those types of things affecting the durability of your liner. So here's an example of an exposure to temperature and UV degrading the polymer over time. You see a reinforced polypropylene basically becoming failing. The resin is failing as it ages here. Here's a mechanical failure, a contraction of the pond liner in a cold event, ripped the extrusion weld right off the perimeter where it welded to a concrete embedment. So the thermal contraction stresses. Here's a physical durability issue with hail. You can see where the hail marks caused penetrations in the liner. It's wicking up moisture from the subgrade, so you can see the dark spots where the hail has caused damage. Then how do you protect against this? A tornado picking up a Connex box and throwing it against the liner system, okay? Of course, the only way that you could have protected the liner in that case would be with ballast protection. Otherwise, there's no way, no liner would survive a flying Connex box. So all of this discussion is focused on how do you choose which type of geomembrane you would choose for your pond. There's a host of geomembranes available. I list across the top a few in this theoretical matrix. You have to consider such a matrix as a concept. I see very few people in practice actually utilizing a matrix like this, but it gives you a framework where on the left side you have all of the properties that you're interested in your liner. Across the top you have your various liner types, and you sort of can weight the different factors and grade them and come up with your most desirable liner. Often what's done is there's a certain set of standard liners that are available, and people look at the cost and the availability and the durability and effectively perform that matrix, but maybe in a slightly different fashion. These 4 bullets, though, suggest what I would look for generically if you're looking for a liner. I have a very good comment here. Somebody says bituminous geomembranes are missing. Yes, I didn't intend this to be complete. I think bituminous geomembranes could be fantastic. I haven't had the opportunity to use them, so let's make special mention that those are definitely valid on the list. I have another question. What's the durability of an exposed geomembrane against UV light? 100 years? 200 years? Question mark, question mark. Recently, there's been a very good publication by GRI or GSI on the estimated lifetime of various geomembranes. They're coming up with numbers, and it depends a lot on the temperature, okay? But if you're just talking about the resin and it's compatible with the fluids and you're just talking about UV, they're coming up with numbers in multi-decades, 30 years, 40 years, 50 years for different kinds of resins. In general, I would amortize your liner over 20 years. That's my recommendation. And you'll find many pond liners will outlast that. I have ponds that I designed 25 years ago that are still in service. And there's other examples in the industry of that. But I would not recommend, at this point, a useful pond life of much more than 20 years. It's simply a prudent way to go. But in fact, it looks like we have various types of liners going towards 30 years. We have EPDM roofs that have certainly lasted more than 30 years, for example. Anyways, back to my point. First of all, your liner has to be chemically compatible. If you get solutions with a lot of chlorine or hydrocarbons or different kinds of other types of chemicals and different kinds of industry facilities, high acid, high bases, etc., you want to make sure the liner you select is proven and compatible. I recommend you use a product that has recognized industry standards for the type of resin, for the type of additives to protect against long-term oxidation and UV protection, and that these standards are recognized related to exposure and durability. The third bullet is a key one. The material must be repairable. There's a lot of things that are probably closer to tarps that are being promoted. Of course, people make tarps. Tarps are a very good thing. But if you use something that's a tarp for a pond liner, you might be able to install it and you might even be able to weld it. But try coming back 4 years later when it's been exposed to UV, oxidation, temperatures, mud, dirt, chemicals, and you have to repair it. Can you repair it? That is a critical question for what I would consider a real pond liner. And lastly, warranties. A good liner should have, you can ask for a certain level of warranty. Of course, you sort of pay for these things. Warranties, you generally see them for the material in the 5 to 20 year range. Some manufacturers I've seen will have a sliding scale of warranties. If you buy a thicker material, they'll give you a longer warranty. If you pay more money for the material, they'll give you a longer warranty. All right. It's good to ask for a warranty about being able to repair it after a certain number of years. Why not? You should be able to get assurances you'll be able to repair it. Installation warranties are generally good only for a year, so you want to check out after you cycle through some extreme temperature cycles, do a good inspection of your pond within the first year. Be careful of new products that are outside of the box that have initial cost savings. You should, if you're going to use them, they need more technical evaluation, and will somebody stand behind it? Okay, examples of types of geomembranes. This is not an exhaustive list. Somebody already pointed out I left out bituminous geomembranes. These are common geomembranes by type. Flexible reinforced geomembranes. The most common ones are polypropylene, chlorosulfonated polyethylene, CSPE, which the most famous trade name was Hypalon. Ethylene interpolymer alloy, EIA. Just one of the trade names is Siemens Corporation XR3, XR5, but there are others. I'm not promoting any brand. These are just, those materials are also available unreinforced, by the way, but more commonly you find those particular materials in a reinforced roll good. EPDM, which is basically a synthetic rubber, is most commonly unreinforced, but also it is available in a reinforced product as well. But most commonly it's unreinforced, and it's used for certain ponds. It has poor hydrocarbon compatibility though, but in other types of ponds it's used. PVC with many different types of formulations has been used perhaps longer than any other material. It's used on vast brine concentration ponds around the world. The formulations vary quite a bit into whether it can be exposed to sun. A lot of formulations need to be covered. Some formulations, especially from what I've seen for big reservoirs and dams in Europe, have been allowed to be exposed. There are spray-on liners, typically polyurea, also polyurethane, two-part mixes that come out of the gun and then solidify with different cure times. Then, of course, there's polyethylene, which is typically the most common, the most prevalent geomembrane used in the world. For right or wrong, good or bad, it simply is. It's definitely not my favorite material to install. It has all kinds of problems with wrinkles, expansion, and contraction, but it has great chemical resistance overall. The cost is very competitive. But it's a real bugger to install and to work with in an exposed fashion. As we mentioned, bituminous membranes, they're very thick, very durable, lay flat, and they've been around and proven. There's different formulations have been used. Again, I don't have personal experience with them. They could be very useful. With all of these, thicker is always better. Thicker will last longer. It'll be more durable from an aging point of view and more durable from a mechanical point of view. Somebody says GCLs below geomembranes are not mentioned. I would say GCLs or clay liners below geomembranes are probably not useful unless the liner is ballasted. In an exposed geomembrane situation, a composite liner is not effective. The clay component of the GCL or the physical clay will degrade in an exposed unless the geomembrane is ballasted. Okay, I've seen it. That's my opinion. Okay. Somebody else had a question on how can we get rid of existing whales. I'm going to save that one till the end. Okay, somebody else asked, how does gels in the polymer affect the durability of the membrane HDPE specifically? I guess a gel is a blemish, if I understand the question, and any blemish in the geomembrane is a potential point of weakness. You shouldn't be seeing gels in your geomembrane, if I understand what you mean by gels. Okay, I'll move on. just a few pictures, atmospheric pictures of different geomembranes. Here's a floating cover. Floating covers are commonly made from reinforced, flexible geomembranes, especially in the potable water industry. This one's polypropylene. Usually you put the floating cover in normally when the pond is empty, it lays flat, and as the pond fills up, it goes up and down with the water level, and the excess slack is usually taken up with weight tubes. So that's what this shows. Here's a very old installation in the United States. To my knowledge, it's still in service 45 years later in Moab, near Salt Lake, for evaporating ponds to reclaim salt. They're lined with PVC. The perimeter berms are covered with hypalon because the PVC was not meant for exposure to the sun, but if it's covered with salt, it's fine, but the berms were hypalon. So that's a testament, 45 years old. There are very, very large solar evaporation ponds for salt reclamation in the Atacama Desert, and the geomembrane of choice is PVC in those locations. Here's an example of EPDM, flexible, non-reinforced. It appears to be a stormwater pond application. A spray-on liner, again, typically polyurea, also polyurethane. You can adjust the set time. You can spray on, or you can sprinkle on coarse sand to make it textured. You often spray it on top of a geotextile. It adheres very well to prepared steel and concrete surfaces. And it's typically expensive and often used in decorative ponds. Polyethylene. Here's a pond, double-lined pond with polyethylene. The crumpled up stuff on the right side is simply a cover that's inflated during the winter time. Polyethylene's popular for, it's got a great track record, durability, cost, repairability, availability of textured surfaces. But I think it has terrible issues with wrinkles, and stress cracking is still, that's ultimately the failure mechanism of polyethylene. It's ultimately going to be stress cracking and at the end of the day. And so there's been giant strides with polyethylene, and I use a lot of it, but it is the problem. And the extrusion welding seams are just an endemic problem. Seams in all liners are a problem, folks. Don't kid yourself. And the fusion seams are pretty good in polyethylene, but the extrusion welding is definitely a weak link. When do I use LLDPE over HDPE? That's a question. For ponds, I guess I haven't. All right, I've always used HDPE in ponds, but I use LLDPE in other situations, in heap leach pads and landfill covers. It seems that the HDPE has a better exposure durability rating. I guess that's the bottom line. But maybe other people would have a comment on using LLDPE for ponds. I know medium density polyethylene is promoted quite a bit by various manufacturers for pond liners, maybe that wouldn't have quite the longevity. So I don't have a very good answer for that question. I think it's something that somebody could look into. Generically, HDPE will pencil out better in terms of its exposure durability. Okay, so I'm going to leave it at that for answering that question. Okay. Somebody asked a question earlier about waves, what to do about wave action. And this part of the presentation has to do with the waves that create this kind of damage, which is deforming the soil under the geomembrane due to the wave energy. This is a slide from 35 years ago from J.P. Giroud. This is not a new issue. And I have many other projects I could show slides of. It's a common issue. How do you protect against wave action on the perimeter slopes? Okay, the best mitigation by far, if you know it might be, your soils might be susceptible to it. If you have a long fetch distance and you have sandy soils, the best solution is to do cement treatment. Add, 8% cement or something to your sand in the upper 6 to 12 inches. Yes, it's a cost, but that will solve the problem. There's other ways. You could put cement-filled geo-webs underneath the liner and then cushion the top of those. If it's a really clayey soil and you're afraid of it, you might use lime instead of cement. Of course, we talked about ballast protection, using the proper cushion and then covering it with concrete slabs, articulated concrete blocks, good old-fashioned riprap, cement-filled geocells, grout-filled geotextile mattresses. All these types of protections could be used. If you're just trying to count on your embankment soils to resist the wave action, many people do, it's good to have something that has cohesion. If you just have a cohesionless sand or silt, it's going to deform over time due to waves. A loam, something that has sand and silt and clay, provides good structure and good cohesion to maintain that shape. Of course, a flatter slope is always going to be a little more stable than a steeper slope, stable on a global and on a micro level, okay? Now, some people think if you do increased compaction of the surface soils, that will help protect the soils by making them denser and more compact. True, yes, but long-term, the pedology or soil morphology of superficial soils, you can't count on that compaction. There's freeze-thaw, there's the fluttering action of the soils, there's wet-dry soils. There's a lot of wet-dry cycles, folks, that goes on beneath the geomembrane, okay? Over time, that's going to loosen the superficial soils, so you cannot necessarily count on compaction to stay there. There's other techniques that could be explored. Floating booms and tensioned curtains to dissipate the wave energy. Those have occurred. A big exacerbating influence is leaks or saturation caused by other mechanisms. When the soil underneath the liner gets saturated due to leaks, due to infiltration through the crest of the berm, due to wet-dry cycles, vaporizing water and condensing at night and saturating parts of the slope locally, or an adjacent pond that leaks water through the berm between two ponds. When that soil becomes saturated, it's more susceptible to wave action. Okay? So that's my talk on that subject. I hope it answered the question. What about benching of pond slopes? I don't know. I haven't benched pond slopes except maybe to put an access road down. The access road is a sort of, I guess you could do some kind of a reinforced benching of the soils below, but benching is going to create bridging points. And so now you got to look at your geomembrane bridging over benching. I don't see benched pond slopes, and if you do bench it, you have to anchor the liner at the toe, on the inside toe of each bench, and then come over the bench, and it seems to greatly complicate it. Ponds and reservoirs that are lined are typically not benched. Okay, we're coming in on the last section of the presentation. We have 15 minutes left, and I still have one unanswered question I hope to get to. Pond operations. Okay, when you turn the pond over to the owner, the level of protection of the liner has to be commensurate with the equipment that's going to be used in the ponds. If they're going to throw in pumps or set pumps, if they're going to use aerators, there need to be landing pads for these pieces of equipment and not just a rub sheet. I mean, you need a piece of concrete or a gravel pad. If you're going to launch boats, you need surfaces that are durable. This is where ballast comes in and helps. the operator has to be made sensitive to the physical durability limits of the liner. Our liner materials, geosynthetics, have really solved a lot of problems. They're great and they're tough, but they do have a limited durability. It's not like an old asphalt or concrete pond where the operator is working on those types of surfaces. No, if they're going to use boats and equipment, they have to respect the liner. There's so many examples of ponds that have failed because the operators simply were not told to be careful. All right. And if they do damage the liner, they shouldn't hush hush and be quiet about it. They should be encouraged as soon as possible, report a damaged liner so it can be fixed, because a damaged liner just makes life, it gets worse. If you're going to clean a pond, of course, that has to be thought about with great care. Rubber boots, rubber squeegees, how you slurry up the sludges and suck them out, and all of that needs to be thought about with respect to the type of liner you have. Any entry and exit from the pond has to be thought out intelligently. Okay. This next point is one of the most important points. If you've gone to the trouble of doing a double-lined pond and you have a leakage management layer between the two liners, you have to monitor it and manage it. Otherwise, it doesn't exist and you wasted the money. There's been most of the litigation I do with containment systems is about ponds. It's not about landfills. It is there, but it's mostly about ponds because ponds are exposed and everybody thinks they're simple. They are simple, but you have to respect certain principles, and this is one of them. So you must have continuous monitoring and management of your leakage detection layer. Then go ahead and do regular visual inspections, look for obvious damage, look for slope deformation due to waves, look for animal problems, discoloration, different things. You can put fences. Ponds are commonly fenced to keep out people and to keep out animals, big animals. You can do electric leak location surveys. You can start out with a conductive liner, or you can have you can do it on full ponds, and you can try to set your system up. Maybe you do it at quarter points in the life, because these can be expensive surveys. Maybe you do it halfway through the pond life, or 2/3 of the way through the pond life, or when you know you have a big leak, you do these types of surveys to find the leak. Bubbles in ponds cannot be ignored. If you see a bubble, and this is maybe the time to address the question, if the bubble is stuck and it's not moving, you have to try to push it. You can try to do it from a boat, or you can put on waders and push it manually. The fuller the pond is, the greater the internal pressure and the stiffer the bubble is. And in my papers, I actually do example calculations that it blows your mind how much force it takes to move a bubble. If it doesn't move, you have to lower the water level until the bubble becomes loose and non-stiff. In a loose state, you should be able to work the bubble. Maybe you can split it and move it, and you move it towards the perimeter, and then it should burp. It should go up the side slope, and you have to, of course, have a perimeter vent at the crest of the slope. That's what you do with bubbles. There have been cases where people have drilled a hole in the bubble and welded on a penetration, essentially, with a little PVC pipe with a valve, and you bleed the bubble till it sets down on the bottom, and then you can close the valve. So that's been done as well. Okay, so I hope that answered that question, but you don't ignore the bubble. You shouldn't. If the water goes over the top of the bubble, things aren't going to get any worse. okay? But as long as the water is getting higher and you can still see the bubble, it's getting worse and worse and worse in terms of pressure and stress and strain. And you can fail the geomembrane. It's happened. It's happened under those slides I showed before. Those bubbles, they burst. Not a big, dramatic, loud noise like in the laboratory. No, just it simply fails. And if you have high groundwater, of course, that requires special considerations. You should have designed for that ahead of time. If you didn't, and your pond is uplifting, you may have to use ballast, or you may have to do a perimeter drain to artificially lower the groundwater. Otherwise, you're going to live with a liner that goes up and down due to groundwater. Well, okay, so we did it. We made it through the presentation. I think I answered all the questions that came through. Now I see another one that just came through. A couple more. Okay, so one says, can you share the connection details between the liner and HDPE pipe with us? Anytime you do a penetration, it's a very delicate thing to design, to specify, and really we're at the mercy of the installer. There is one ASTM standard about penetration, and there's one paper I wrote in 2009, and it was presented at the Geosynthetics conference in Salt Lake City. There is very little information on doing good penetrations. They're a work of art. You always want to have redundancy. You always want to have the free field geomembrane bolted or welded to a fixed plate or a concrete pedestal, and then have your environmental boot stress-free over that. The trickiest weld is always the sleeve to skirt connection, and we could talk for another half an hour just about boots. So you need to pay attention to those details. Okay, let's see. We got a couple other questions going on here. If I can. How do you feel about? Sorry, here I'm just having problems stabilizing this. Sand tube ballasting system. You'll get partial ballasting with sand tubes. Those will work. Those will be partially beneficial against wind loading. They'll probably be very weak against hydrostatic uplift. Okay, and they're spaced every so often, so they're not going to help you a lot with all the other benefits of ballasting. So sand tube ballasting, yes, great for some limited wind protection. And that's it. And you can calculate the wind protection they offer by looking at the references of Giroud. But yeah, I think sandbag and sand tube protection for wind is good, but that's about the limit of its benefit. What's the reference for vent spacing? Excellent question. There's no reference. There's only a standard of practice. When I said 50 to 75 feet or 100 feet, which is what, 15 to 30 meters spacing on vents, there's no reference. It would be great if somebody could actually calculate that. I have not yet succeeded in calculating that, and so we simply go with industry standard on the vent spacing. Okay, another question. I'd like to know more about textured liner and textured liner being used to create a leakage or gas management layer. There's nothing more to know. Take it to a laboratory, test it. You can measure the transmissivity. Realize one thing though, liquids and gases are not compatible for draining. You're pretty much doing one or the other at a particular location. However, if the liquids go down, that allows the gases to go up. But you can measure the transmissivity in the laboratory and you can see if it suits your need. And like I say, I've got a case history where it worked very elegantly. Should the drainage composite Sorry, I'm just having a little problem with managing my scroll back here. Should the drainage composite be rigid? 2 geotextiles with a geonet core or flexible? I don't consider a geonet too rigid, so I think it's just fine, and I think a flexible one is just fine. Many ponds have been constructed with a geocomposite geonet, you know, a semi-rigid. It's not totally rigid. It's a standard biplanar geonet is just fine. Also pay attention to anchorage of the pipe. Good compaction, concrete footings to ensure that the pipe is not moving. Yes, yes, yes. There's many details we could go on about penetration details. Comment on the gel blemish. A blemish that affects physical properties of a geomembrane is an issue. It is common to be able to see visual blemishes after deployment that do not indicate harm to a geomembrane. Okay, well, I'm not going to get in the blemish issue. If you do have blemishes, you probably want to question them, but it's outside the limits of this discussion. Thank you, Boyd, for that comment. Is there a place where we could download the presentation slides? Well, guess what? I'm going to sign off now. Thank you all for listening, and I'm going to let Richard Brockman answer about downloading the presentation slides, and he'll give some closing thoughts. It's been an honor to talk to you, my colleagues from around the world. I guess we had 58 attendees. Thank you very much. Good day.
This is Richard Brackman back here. Just to wrap things up, first of all, Rick, thank you very much for the time, for summarizing your experience, your insight on a very important topic. On the surface, it looks quite simple and straightforward, but just like all things, the devil's in the details, and keen engineering and a thoughtful mind is a useful way and a practical way of managing these sorts of issues. So thank you very much for sharing that with us. In terms of follow-up materials about accessing the slides, we'll follow up with you to the attendees with an email. And now taking a quick look at the clock, we're going to call this webinar to a close. Please pay attention to your email and our website for our next technical webinar. Thank you very much, everybody, and have a great day.